are doing written homework, sometimes it'll get a little complicated in terms of what I'm assigning. I'll make it as clear as, very clear, but there's like multiple sections and multiple problems in each section. So here's how you want to, when you have your presentation of what you're writing on your own paper, it has to follow this. I'm not going to read through it. I'm going to let you read through it. So the first time this is going to kind of apply is Monday, because you're going to be doing actual problems from the online text. And so get in the habit, just start on Monday, get in the habit of this format, okay? So I'm not going to read it to you. I'll leave it to you to read it. And then if yours is drastically different than this, then you could lose some points. You could be deducted points, okay? So follow these guidelines, please, on homework. This will be very helpful for the graders and then for your own organization, okay? Let's just jump right in. Oh, so the homework that's due today, we'll hold on to it and we'll turn it in all together with Monday's homework. I've also, because I think maybe today's class might clear up some things. You can make some revisions. You can ask us questions today by email or after class. I've also posted Wednesday's homework. So if you want to start on that this weekend also. So what's due today along with what I assigned for Monday, so let's look at that. So we'll just group these two together, Friday and Monday. We'll turn that in Monday. And then Wednesday's post is already there, okay? If you want to recommend that you get started on it this weekend also. Okay, let's jump right in. So we were doing this. And we're in this endeavor. You know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. How do we know how fast a quantity is changing at every moment? What kind of thing would we have that we would know how fast a quantity is changing at every moment? What would that be? A rate of change function, right? And so this graph is a representation of this rate of change of the height of the flag. So there's this a sequence of functions that we work through in order to solve this problem. You know how fast something is changing every moment. You want to know how much of it you have. So that starts with the exact rate of change function. And what are we after? So in the very end, so before we go through talk through the progress, what do we want in the end? What do we want? So from exact rate, so you know how fast something is changing at every moment. You want to know what? How much of it you have at every moment. What's that going to be? So mathematically, what are we going to produce that's going to tell us how much we have at every moment? Right, so it could be net or total accumulation. We haven't talked much about total accumulation, but it's so close to net accumulation. We'll talk about it today. All right? So these are almost one and the same in terms of you know how much you have. And this is exact, right? Also exact. So we know we have the exact rate of change function. We want the exact accumulation function, whether that's net accumulation, amount of change since the starting point, or total accumulation, just all the stuff that we have, right? All the stuff that we have. Okay, so then the question is, how do we get from A to B? So we were saying from exact rate of change, what are we going to do to make some progress towards net or total accumulation? What do we do this? So what's the? Why can't we just get it? Right off the bat. So I have exact rate of change. What's the roadblock that prevents us from getting net or total accumulation kind of immediately? Changing rate, right? So as soon as a little bit of our x changes, we have a different rate, and so that this is like kind of a roadblock, right? Because to get accumulation from rate, what is our key principle to get accumulation from rate? What's the key principle? Given rate of change called M, how are we going to get net something to do with accumulation? dy, that's a little change in our amount, right? Equals M. So this is the key. But this is dependent upon what? M is constant rate of change. Not changing rate of change, constant rate of change. So we want to use this principle, but we can't use it directly from this function because the rate is continually changing. Make sense? So what do? Yeah, we're going to make like a step function, right? We're going to make a function, a new function that's trying to be like this one. It's like pretending to be like this one, but it consists of constant rates over intervals, right? So we're gonna chop it up into intervals. We're gonna put a constant rate in each interval, so that when you put all those constant rates together, it's trying to be like the exact rate function. I said that really good. Did you hear it? Okay. So we're gonna chop up this into intervals. We're gonna find constant rates in each interval, so that when you put them all together, it's doing its best we can to mimic the exact rate function. Okay, so what we did last time and what you did in your homework was you were eyeballing. You were looking at kind of like, here's the range of rates. Like, what's one constant rate? That's kind of like maybe like the average, if you will. Okay. If we do it that way, then everyone gets something different, right? This should be close, but everyone's going to get something different. So here's another way to do this, to figure out what these steps are going to be, so that we would all get the same thing. Okay, and so what we would do here, let's see, yeah, I'm at 0.35. So rather than looking at each interval and looking at it and trying to eyeball, what if we just picked off the exact rate at the left side of every interval and then just made that the constant rate? What would that look like? It would look like this. So the gray is the original. So now in every interval of 0.35, I'm using the exact rate function to find that exact, to pick off that exact rate, and then just make that the constant rate for the whole interval. And then when you start the new interval, you find the new exact rate at the left side, and let that be the constant rate. So then we get something like that. So now this blue graph is using that method. Rather than an eyeball method, it's what we call a left-hand approach. Left-hand approach meaning pick off, here's an interval, pick off the exact rate on the left side, and then let that be the constant rate through the whole interval. And then we'll all get the same thing, right? It's kind of more systematic, right? Rather than just kind of eyeball. Make sense? Okay, so and we said last time our final goal is this net accumulation. We sketched that. So now what's after? So this is our what? So from exact rate of change function, we do what? We create what? Approximate. That's the blue one. Approximate rate of change. Whether you do it eyeball, whether you eyeball it like you've been doing so far, or use this left-hand approach. You could also use a right-hand approach. You could pick off, use the right rate, make that the constant rate. But in any case, you're creating an approximate rate of change function, what? Consisting of constant rates that are trying to pretend to be the exact rate function. Okay, and now we can use this, right? So the whole point of that, so we made it bad, right? So this blue function, it's not replicating the original function very well at all, right? Kind of, but not great. So why did we make it worse? We had this perfect exact function. Why did we make it worse? So that we can use this now. We can use dy equals mdx at any given place because we've got constant rate through intervals, right? In every given interval, we've got a constant rate. Okay, so that's why we did that. Question? Is that a question? Yeah.
Yeah. I was just wondering, like, how come we didn't take like an average of the parts where we know the rate is changing instead of because like right now what we have is we've chosen some interval.
Yeah.
And we decided to take the average of that.
I'm not following your question.
Okay, so there's some parts where the rates of changes are the rate is like constant.
Yeah.
But there's other parts where like the rates are changing for sure. How come we're just like
so that's just this particular function.
Okay.
This particular function, and it's actually not constant through here.
Oh, it is. Oh,
It just looks like it's so close to constant that it looks like a horizontal line. But that's just this particular function. So just imagine your rate function is truly, I mean, it's clearly changing everywhere. That's kind of the generic case of it. So it just happens that this function, because it's the height of the flag, and you're pulling hand over hand, it looks like that. Does that make sense? Yeah. Okay. Yeah.
Is there a method you prefer to use, like the left end or the average?
We'll use the left from here on out. Yep. But just know, like the eyeball method is the idea of it, right? The eyeball is like, okay, we're trying to make it be like the function. Okay, because the eyeball method, like for this interval size, would do better than this, right? This isn't doing very well because as soon as you come off the left side, the rate changes, and so then it's not as good. But that's okay for now. All right, so now we can use, because we have the constant rates, we can use dy equals mdx, and we create what next? From the approximate rate of change function, now we can use dy equals mdx. We can calculate little dy's, and what kind of function can we make out of the dy's? Approximate accumulation. So let's take a look. For this particular left-hand approach, I'm going to show you what we'll get for the approximate accumulation here. Here it comes. So now this purple graph over here on the right is the accumulation you'd get, what? From the blue function, right? From the approximate rate function. Good or bad? I heard it's not terrible. That's a good answer. It's not terrible, right? But is it exact? Far from exact, right? It's far from. It's certainly not the same, but it's not terrible, right? It's got the same kind of idea, right? It's negative and getting more negative. Starts at 0, okay? But it's definitely not our exact accumulation function that we're after. Okay, so then the question is, this is kind of the progression of things. Given our exact rate function, you know how fast something is changing at every moment. You want to know how much of it you have, the gray one over there. So we've got to use dy equals mdx, we've got to make our pretend rate function out of constant rates. And then from that, we can build the approximate accumulation function. That's kind of what we'll talk about today, doing that. So then the last kind of missing link here is, how do we get exact net accumulation out of approximate accumulation? So if this is approximate, then what's it going to look like to get something better or get the exact accumulation? So what's the mathematics behind going from the purple graph to kind of converging on the gray graph over there? What do we need to do? Right, so it's smaller intervals, right? So if I make, and here, just do this. Watch this. This is why graphing calculator is so great. I can just, with a click of a button, I can make the interval smaller. So this is 0.35. This is 0.1617. Your TI is not going to be able to do that, okay? All right, I'll make it so then, look, so now look at the approximate rate function. Better or worse? It's better. And therefore, approximate accumulation function, better or worse? Much better. So with smaller intervals, it's like we can get a better approximate rate function, and so we can get a better approximate accumulation function. But we want exact. So how are we going to get exact? Yeah? Yeah, super small, right? The smaller that we make it, so here is 0.0395. And so now look at that rate function. It's doing a very good job of replicating the exact rate function. And then the approximate accumulation function, we almost can't tell the difference now. So let's go to super small. So super small means, here's 0.005. All right, so on the left, is that approximate or exact rate of change? On the left, the blue one here, approximate or exact rate of change? Still approximate, but do you see, like, if you move back a little further and blurred your eyes, you really wouldn't be able to tell the difference. But if I come in here and I zoom in, Still little constant rates, just over really small intervals. Okay? But the idea is, the smaller that you get to a point where you can't tell the difference anymore. And it's that point where you can't tell the difference anymore that we call it a day, right? We call it a day and say, okay, that's good enough. And now look at your approximate accumulation function now. Right? Now it's close enough that we call it a day. Okay? Okay, so questions on this before we move on to the next example. Can you guys hand these out? So let's review let's go back to we had our set of principles. So let's review that. If I can find that. So just hold on to that, put that sheet to the side just for a second. Let's just talk through this. Principle 1 was constant rate of change, right? What does 60 miles per hour mean? Does it mean that in 1 hour you go 60 miles? Is that what 60 miles means? Every hour you go 60 miles. That's a good meaning for that. It's true, but is it a good meaning? No, what's a good meaning? What does 60 miles per hour tell you? A lot more than how far you go in 1 hour.
For any change in the unit of time,
Yep.
you travel 60 times.
It tells you how far you go in any amount of time, not just an hour, right? And that is exactly what dy equals mdx is. dx is any amount of time that you want. The 60 then will tell you how much change in distance you go. Everyone will get one. Just focus on me. I'll make sure you get a sheet. Just focus up here, okay? So, or just raise your hand and listen. Just raise your hand and listen if you don't have one. Yeah, so the fact, yes, 60 miles an hour means that you go 60 miles in 1 hour. That's a very narrow meaning. Very narrow meaning, right? You know how far you'd go in any amount of time. That's what dy equals mdx is. Given any change in time, dx, multiplied by 60, you get the change in distance. For any change, the change in distance is 60 times the change in time. Okay? Constant rate of change. This is like the foundation of this whole journey, right? It's the key thing that gets us from rate to accumulation. That's the key principle that gets us from rate to accumulation. Okay? Net accumulation function means that you know how fast something is changing at any moment, right? Net accumulation function is you know how much you have at any moment, okay? It gives you the amount of change since the starting point. A net accumulation function, the amount of change since the starting point. Changing rate of change. Oftentimes, a realistic rate of change is going to change. It's a changing rate, right? Changing rate. Principle 4. We build a pretend rate function out of the exact rate function. So we're trying to mimic the rate function with constant rates. And apply number 1 to estimate amounts of change. Okay, so what's principle 5? So just forget about that for a second. Principle number 5 is make more smaller intervals, right? Make more smaller intervals to get exact rate. No, to make it better, right? To make the approximation, the rate approximation better, and so the accumulation approximation better. So better pretend rate function means better estimates of net accumulation. Okay? Better ingredients, better pizza. All right, so that's what we've talked about so far. So let's look at this. I don't work for Papa John's. Let's look at a new example here. So this is what we're going to be looking at in your worksheet. So this is unloading sand onto a scale. here is the exact rate function. I'm calling it R sub W, and it's rate of change of weight with respect to time in seconds. Still need one? I'll get you. All right. All right. So rate of change of weight with respect to time in seconds. This is exact, and so we use R sub W, where so W is like the weight function that we're after in the very end, right? Weight would be like how much you have at every moment. So that sub W is saying that's what our goal is, to get that W function in the end. Okay, so I put the units on there, seconds on both horizontal axes, right? Time since unloading started. And then your unit on the left graph is 100 pounds per second, rate of change, right? And then for accumulation, it'll be hundreds of pounds, right? 100 pounds, 200 pounds, 300 pounds, hundreds of pounds. For a sketch of our final product, it looks something like this, right? So just a quick sketch, right? This is not exact, but just to get an idea of what we're headed for. So should it go down somewhere? Should the accumulation of weight go down? Why not? Yeah, so is the weight going up or down right now? Still up. Do you see that the weight is still going up even over here? Because the rate is positive, right? The rate is positive. So it's just going up at a slower and slower rate, but it's still going up. Remember, this is rate of change. So our net accumulation will look like that. So, or is that net accumulation or total accumulation? It's net, right? At time 0, we have 0 change. How could total be different? Why would total maybe be different than this? Yeah, like if there was sand already on the scale before we started. So then maybe at time 0, total weight would be like up here. Maybe there's 250 pounds on the scale already. And then from there, we start accumulating according to the new dump, right? Okay, so the net accumulation, which means at our starting point we have 0 change. So this function is giving us change in weight at any time, right? Change since the beginning. And then what we're really after then is W, which is total weight on the scale. All right, so let's look at number 5. Let's pick up with number 5. If you haven't, just go straight to number 5 if you haven't got there yet. Just about like 3 minutes. 3 minutes. Okay, so here are these rates, right? So this is what your sketch should look like, using the exact rates at the left side of every interval. So now in part A, it says it's talking about what. There we go. So the question is, how do we represent these values exactly? So yeah, this one's a little bit greater than 1, but how can I represent it exactly? What can I write that represents that exact rate of change right there? What can I write? What is it? Right, so where this comes from, it comes from the exact rate right there. What is the exact rate right there? What is the exact rate for that point on the graph right there? What's that exact rate? R sub W of 0.3. That's a representation of that exact rate that we're using as a constant rate for the whole interval. We got it just from the left side, but now we use it as a constant rate for the whole interval. Okay, so what's the exact representation of this one in the third interval? So how do I express that constant rate right there? R sub W of 0.6. Doesn't make sense. Function notation, right? Represents a value of the dependent variable. That's what we're talking about. The dependent variable here is rate of change, right? So I can represent that rate right there as R sub W of 0.6 because the x value is 0.6, and that's what the rate we'll use for the whole interval in our approximate rate function, etc. So then you've got the others too. So that's just the second and third intervals. That's what our function will be, the second and third intervals. All right, so now what's the approximate accumulation at 0.8 seconds? So I'm going to stop here I'm going to come down here. I'm going to, at 0.8. Right there. So we're going to pause it, right? So we show it emerging like this, the way I'm showing the graph dynamically, because there was some time when the sand was being unloaded and these points on this graph were generated one at a time. But now we're going to freeze time and just talk about this situation at 0.8 seconds. And I want to write what is my net accumulation, an expression for my net accumulation at 0.8 seconds. So in other words, I want to write what A of 0.8 is. A of 0.8. How do I do it? How am I going to come up with the amount of change of sand in hundreds of pounds starting from time 0? So what was the key? Key principle is constant rate of change, or dy equals mdx. But I've got to do it one interval at a time. So in this first interval, what's my m? R sub w of 0 times 0.3. That's the little bit of change in weight, m dx, for that first interval. Then, but that's only how much change we have after 0.3 seconds. We want 0.8. So what do? We're going to add on the accumulation we get in the second interval, which is R sub w of 0.3 times 0.06? No, it's still 0.03, right? It's just the amount of change at that rate. So that rate is still, that rate extends through the second interval, which is a change of 0.3. Okay, and then plus RW of 0.6 times 0.3 again, right? No, so this is what we call the current interval, and we haven't finished it yet. It's not completed. So really, we haven't got a full dx. We only have 0.2 of that. So we want times 0.2 this time. So this is the general structure of the approximate accumulation function. We're going to use mdx for every completed interval, and then we're going to have a little bit more change for a partial interval, or the current interval. All right? So this right here is what we call completed intervals. And this is for the current interval, which is like a partial interval. If we freeze time, if we freeze the x value somewhere in the middle, which most likely it'll just get frozen somewhere in the middle, then we haven't done a full interval yet, and that's what we call the current interval. So this is the general structure of our approximate accumulation function. The sum of accumulation, sum of changes from completed intervals plus a little more change from the current interval. So now what if this was 0.03? What if our delta x was 0.03 and we were going to x equals 0.8? What would this look like? A lot more intervals, right? I'd have, 10 times as many. I'd have 20 intervals. So we don't want to write all those out, because we know we're going to make it smaller, right? We're going to make it smaller. When we do that, we don't want to write that out. But notice they all look the same. So let's just write it out once. Just write it out once. R sub w of, say, the ith, x of ith, left side of the ith interval, always times 0.03, right? And then this symbol is just going to mean do a bunch of them. Sum up a bunch of them. That's Greek sigma for sum. I'm going to sum up a bunch of these. Right? Each one looks like that, right? It's going to be some rate from the exact rate function times 0.3. And we just keep doing that over and over again. So then we just let I go from, say, the first interval to the number of completed intervals. How many total completed intervals there are. And then we'll have plus the rate in the current interval times, so this this amount of change in the current interval is actually what we're going to use for dx. So dx is a variable. It varies through the current interval. It starts at 0, and it varies and increases to delta x. So this is the structure of our. Sorry, this is delta x, right? So this is just that 0.3. That's just our delta x. So this is the structure of our approximate accumulation function. Interval by interval, we're going to take that constant rate times the change, which is always delta x. And we're just going to keep adding. Constant rate times the change. Constant rate times the change. And then we'll have a little bit more change due to how far we've gone in the current interval. And then what are we going to do? So that's our approximate rate function. Okay? And how do we get the exact rate function? What do we do? We're going to let delta x what? Get super small. And that's going to give us what we call our AWX, which is the gray one that we sketched. Right? If you let delta x get super small, then this also will give us the exact rate function when delta x is super small. All right, let's summarize it. Here we go. Any questions on that? Anybody have a question? All right, so let's summarize. Get rid of that. So here's what we said, right? Red function. So what's the progression? By color, right? By color. You know how fast something is changing every moment. You want to know how much you have. What's the progression by color? First one is red. Exact rate of change. Then approximate rate of change. Blue one. Then purple is our accumulation function based on the blue step function. Finally, black. As you make the intervals real small, that approximate function will converge on what we imagined in the beginning as the exact accumulation. Okay? So the approximate net accumulation function we said is this. This is, so don't lose sight of, this is just summing up a bunch of dy's, each one calculated by m dx, or m delta. So a bunch by m delta x, which is a change in x, plus a little bit more for the current interval. But it's just summing up changes by m change in x, m change in x, m change in x, just adding them up. Accumulation, adding bit by bit. And that's the mathematical way to say that. Okay? So to get exact accumulation, exact net accumulation, that's when you have that thing and your delta x is super small. But we have a more compact notation for that, more succinct. Does anybody know what it is? Integral, right? So when delta x is super small, that top function, we rewrite it as the second function, integral, right? So Greek sigma means, what does it mean? Sum. German S means sum. So summing up a bunch of changes, right? M dx. Same thing. Here's the rate function times little change in x, right? So summing up a bunch of changes in y as x increases. And so that gives us our net accumulation function. Okay, so suppose that there were p 100 pounds of sand on the scale to start with. Then what would the W function be? What would W function be if we started off with p 100 pounds of sand? P plus that, right? It'd be P plus that would be your W function. So here's total weight on the scale. Everything you had from before, P, plus the accumulated changes as time goes by, right? All right, so we made it, right? You know, so here it is. Here's our Where do you see, you know how fast it's changing at every moment? Where's that? You know how fast it's changing at every moment? R sub W of t. And you want to know how much of you have at every moment. Where's that? W, right? Or this whole thing, right? So if you know how fast it's changing at every moment, you can write then an expression for how much you have at every moment by writing starting amount plus your accumulated changes, which is the integral of your rate function dt. So when you're in Calc 1, you're doing integrals. Did you know whenever you did an integral? Did you know this was a rate of change function? Oh, good, I'm glad. But whenever you did an integral, that was a rate of change function. That's what that was. And you were accumulating changes by doing rate times dx and adding them all up. See you Monday.